Good afternoon, all. Let us wait for 2 minutes for others to join the session. Then we'll start our lab session. Okay, once again, good afternoon to all. And now I think most of the students have joined, and those who are not here, they will come and join. Let us we start our today's session. Okay. So in the last lab session, if you remember, we have completed our eighth experiment, and today in our session we are going to start with experiment number 9. And we also try to complete the experiment number 10 also, because we have the shorter period of time. So today we try to complete our both the experiment 9 and 10, and in next coming lab we can start our regular sessions also in that time, right? That's why. So let us begin with the first experiment number 9. So experiment number 9, the aim is here on your screen, you can see that, to verify the truth table and timing diagram for NOR gate latch using NOR gate IC, and analyze the circuit of NOR gate latch with the help of LED displays. In short, the aim of our today's experiment number 9, that is to understand a latch, digital latch, or you can say a component of the sequential logic circuit, that is we are knowing as a latch. So let us move inside to discuss this part. So what do you mean by latch? Anybody having any idea about the latch? Yes, any one of you have any idea about latch, or have you heard anything about flip flop? Yes, anybody from your side? Yes or no? No one is replying here, so I can understand there is no any word latch or flip flop familiar to you, right? So let us me tell you about that. First of all, what do you mean by a latch? So latch is, you can say, a smallest unit, or you can say smallest component of any sequential logic circuit. Before we have started to discuss about this digital part, you get familiar with that. There are two types of digital circuits. One digital circuit, that is we call it as a combinational logic circuit, in which we are having various combination of logic gates, right? Like we have discussed about half adder, full adder, half subtractor, full subtractor, multiplexer, demultiplexer, encoder, decoder. So there are various circuits we already have discussed. So these all circuits are developed by using combination of the various logical gates, and that is why it is called combinational logic circuit. But if you have marked the thing in that all logical and combinational circuit, your output of the circuit only depends on that particular input given on that circuit. It means in a combinational logic circuit, whenever you are measuring your output, it is only depending on the present state of input coming on that circuit. What I mean to say by this is, if I just take you here and let us me draw one circuit here. Suppose, let us say this is one small circuit you have, okay, and that is, let us say this is your combinational logic circuit. Okay. Now, what this combinational logic circuit will have, it will have some number of inputs. Whatever input is here, let us say something A, B, C, or whatever number of inputs you have. Right now, I'm just taking 3 inputs. It may be many more, right? Let's say there is 3 inputs given to you, and the output you are getting something Y over here. So in combinational logic circuit, the value of Y is equal to some Boolean expression, and that Boolean expression will have the variable only ABC. That means it will be having a various type of combinations of your inputs A, B, and C, right? It may be A and B, or A and B, or something like that. There are total different 8 min terms you can have for this 3 input case, and according to that you can have the function over here, and based on that function your output Y of this circuit is only depending on the value of A, B, and C, right? And that is only for the present states. What do I mean by present state? Present state means the time at which I'm getting the value of Y, at that same time what is their value of ABC, that is only affecting your Y at that time, right? What was the value given to ABC in past, that is not going to affect your Y. That is the output of this circuit. That's what the combinational logic circuit is. But in case of sequential logic circuit, if I give you the diagram of sequential logic circuit here, then in sequential logic circuit we'll do have some inputs here, right? It will be giving you some output here, but this input and output, let us say input A here, input B here, whatever input C or number of inputs you are giving, your output Y is here, but this output is also given to some part, that is what we call it as a memory, right? What was the past output, that is going to be recorded in the memory, and then memory will be also connected to the input side. Means your input signals are also or you can say your circuit will be also taking your memory signals. That means what was the last output, right? So here this is what your sequential circuit is. In sequential circuit, what we have to do is sequential logic circuit will have combination of a logic gate as well as a memory unit, and that is why the output Y of this sequential logic circuit will also depend on the past output. That means here Y is not only depending on your inputs A and B, it is also depending on what was the input A and B in past, right? And that is what the difference between your combinational logic circuit and sequential logic circuit. And so in the combinational logic circuit, if we refer to a smallest block or smallest component, then it is a logic gates like AND or NOT, NAND gate, NOR gate. That is all you can say a small component of your combinational logic circuit. Likewise, when you are referring to a sequential logic circuit, in that the smallest component which we are going to have is the latch, or you can say a flip-flop. Am I making this thing clear to everyone? Hello? Hello, everyone.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, that's fine. So the main thing which we are going to start learning today is a latch. In your experiment number 9, we are going to understand the working of a latch, and then after you can verify it in the virtual lab here, right? As we are doing in the previous experiments also. So what do you mean by a latch? You can just refer here that a latch, right now it is called SR latch, first initial, that is called set reset latch. And what we'll be having with that latch is, it will be having two cross coupled NOR logic gates or two cross coupled NAND logic gates, right? A latch can be developed by using NOR gate also, and it can also be developed using NAND gate. So there is the first thing in your latch, that is a cross coupled either NOR gate or NAND gate. Second thing is that it will be having two inputs, S for set condition and R for reset condition. And the third thing is that it will be having two outputs, Q and Q bar, right? It can be having like this. You just look at here. This is a NOR logic gate. If I just take it here from here to there, let me just take in here. You understand this one? This is a latch. You can see here in a block diagram, it will be shown like this. It will be having a block diagram like this. There will be a two input, that is you can say input R and input S, that is you can say set and reset inputs. It will be having two outputs, that is you can say Q and Q bar. Okay, and this is called SR latch, set reset latch. So this is a simple block diagram, you can say. Now what is internal structure, that you can see here. Inside this block, this kind of circuit will be there. Okay, so this is simply, you can understand that is inside the block, right? So inside the block, what is there? There are two cross coupled NOR gate. You can say this is the NOR gate number 1, this is the NOR gate number 2, and they are cross coupled, means the output of first NOR gate is applied to the input of second NOR gate, and the output of second NOR gate is applied to the input of first NOR gate, like this. And another input to the first NOR gate is your reset input, and another input to the second NOR gate is your set input. Now what do you mean by here set and reset? See, the output Q here, which is getting at the output of this circuit, if it is made logic 1, we call it is a set condition. Okay, if the output Q is having logic 1, then you can say it is a set condition. Now if your output Q is logic 0, you can say it is a reset condition. Okay, so here input R and S, which is standing for reset condition and set condition, is given the name in such a way that this set input here will be applied to make your output Q to logic 1, that is to make your Q to set condition. And likewise your input R here is applied to make your output Q to be resetted, that is to make it to 0. Okay, Now here there are two outputs, Q and Q bar. So that Q and Q bar, they are always complementary to each other. That is, you can say that your output Q is logic 1, then Q bar is always going to be 0. And if your Q is logic 0, then Q bar is always going to be 1, like that. Right? So they are, you can say, complementary to each other. They both never can be 1, they never both can be 0. Is that okay to everyone? Hello? Am I making this part clear, everyone? The introduction?
Yes, sir.
Okay. Now, what is the working of this latch? See, this is what you can say a latch which will work like a 1-bit memory. Like in pen drive, we have something kind of GB, like 1 GB, 2 GB, 4 GB, 8 GB pen drives like there. That is considering a GB, that means a gigabytes, right? And gigabytes, a 1 byte itself carrying 8 bit. In digital, you can say that when there is a total 8 bit get combined, it is called 1 byte. And when there is number of bytes are there, we considering them like megabyte, gigabyte, something like that, kilobyte. Okay. So right now we are talking about smallest part of your digital circuit, and that's why it is considering only 1 bit of information. 1 bit of information means either it can be 0 or it can be 1. So here Q is your memory space, means it is giving you the storage. So your value of Q can be made to be logic 1 or it can be made to equal to 0 based on your required condition. And for that you have to apply your S and R input. If you want to make your Q logic 1, then your input S should be logic 1 and R should be 0. If you want to make your Q should be logic 0, then your R should be logic 1 and S should be 0. When R and S both are 0 0, it will not changing the value of Q. Right? So here you can see the table. The table just below this circuit given here, having two inputs, that is R and S. Right? So here these are the two inputs, that is reset input and set inputs. When both are 0 0, the first condition, when you are giving your R also 0 and S also 0, at that time what will happen? Whatever condition here at the output side of Q, let us say your Q is equal to 1 and Q bar is equal to 0. This is the condition right now if you have. Okay. So in that case, what will happen if you are giving your R equal to 0 and S equal to 0? Then you can see here, you are giving 0 here to the NOR gate and 0 here to this second NOR gate, right? And based on this Q bar condition, this 0 will come here and this Q will come here. Now, what is the table of NOR gate? If you remember truth table of NOR gate, your NOR gate will give you output logic 1 only when your both the inputs are 0, right? So here you can see that your NOR gate number 1 will be getting 0 from this Q bar here and 0 from input R here. So that's why both the inputs are 0, and so you are getting output logic 1. So your Q will remain as it is, no change in that. Okay. And that same one logic will come here. So the second NOR gate is getting 0 and 1 at the input side, and that's why its output remains 0, no change in that also. It means when your R and S both are 0 0, this Qn here is what? Your Qn is the condition at this point at the output terminal here, and Q dash n means it is the output condition here. Right? So these are the two output column. You can say this is your Q output and this is for Q bar. Now if you just refer here Qn condition, then for the 0 0 input condition, your Qn remains Qn minus 1. Now what do you mean by this? Qn means your present output. It is the output at the time when you are measuring. And Qn minus 1, it is what? It is the output which was coming prior to this input you are measuring. I hope you are getting what I mean to say. Qn means it is your present output. Present means right now when you are checking it. So it is a present. And the Qn minus 1 means it was a past. It means before you are getting this output, what was the last output? That's why it is called the past output. Right? So you can see here, when your input R and S both are 0, 0, your Qn, that is the present output, will be same as it was last output, that is your past output, Qn minus 1. You can see that here also. Your Q remains 1 as it is, 0 Q bar will as it is, right? When you are setting your R equal to 0 and S equal to 0. Now, if I give my input R to be equal to 1 and S equal to 0, now what will happen? I'm talking about this condition. When R equal to 1, S equal to 0. So what will happen to here? So here you can see the condition. Let us say prior to this input you have applied, your output Q was 1 and Q bar was 0 again. So what will happen here? Here you can see that as you are giving R equal to 1, so here it is going to be logic 1 at the one input of logic gate number 1, and here Q bar is equal to 0. So this Q bar will come 0 here. So this 0, 1 will do what? It will give you output 0 here, right? Because the NOR gate logic there. And this 0 will come here. So what will happen? This second number NOR gate will get both the 0. So it will be getting output 1. That means this 1 will be now converted to 0, means your output Q will be resetted. And this Q bar which was 0, it will be made logic 1 here. And that's what the condition you can see here. That your Q will be made to 0 and Q bar will be made to logic 1. When you are setting R equal to 1 and S equal to 0. Right? Now, you can take this condition that when you are setting R equal to 0 and S equal to 1. So for that, what will happen? If your R, let me just take a prior condition here. Now let me remove this part. Let us say your Q is 0 initially and Q bar is 1. Okay, let us talk that condition only here first. So let us say I'm having Q equal to logic 0 and Q bar is equal to logic 1. That is the prior condition I have. So in that case, what will happen now? So you can see that this 0 which you are giving at the input of R will come here. So now your R here, it is going to be 0, right? And you are giving S equal to 1. So your R will be 0 here and S equal to 1 over here. So now what will happen? Here, this set input which you are supplying here logic 1, here 1, 0 will make your output 1 here, because there is a, it will be making output 0, not 1, because 1, 0 is there. So NOR gate will give you output 0 and that 0 will come here. So this 0, 0 input to the first NOR gate will give you output logic 1. That means now your Q will be converted from 0 to logic 1, and here 1 to be, it is going to be 0. So that's why this condition is going to be there. Are you getting? So this is how your NOR logic gate SR latch will work. That when you are giving both R and S 0, 0, there is no change in the output state, means your output remain as it is. So you can say it is a no change zone. That is, your output will not change at all, right? For the case your R equal to 0, S equal to 1, your output will be set to be equal to 1. And when R equal to 1 and S equal to 0, your output will be set to equal to 0. That means it will be resetted. But the last condition, that is both are 1, 1. You are keeping S equal to also 1 and R equal to also 1. That is considered as the invalid outputs. Why is that so? Because when you are giving R and S both equal to 1, 1, you will be getting your output Q and Q bar either 0, 0 or 1, 1, and that is you can say unacceptable condition. Okay. So that is considered as a invalid input. So are you getting this working of this SR latch using NOR gate? Or have you any difficulty in understanding this one? Hello? Are you all understanding this? How this SR latch is going to work? Or any difficulty in understanding this one? Hello, everyone. Yes, only Kevin is replying now. What about others?
Understood, sir.
Okay. Okay, I hope that now everyone have understood it. So what I was talking about this latch is, it is called set reset latch. And that is what you can say smallest part of your memory. This is the smallest unit. In the memory, you will be having this kind of latch. So here Q will be your memory space where you are storing your data, right? When I want to store data 1, I will have to supply S equal to 1. When I want to store data 0, I have to supply R equal to 1, right? So this is what a memory unit. And you can see here that your output will depends on present input as well as your output inputs also. Past input also, right? How is that so? Because you can see here we have used the cross coupled NOR gate in the latch. And that is why your input which you are supplying here at R and S is not only changing your output always accordingly, right? Because you can see if your Q is equal to 1 here and you are supplying S equal to 1, then your output will be kept as it is. It will not change it because Q is already set, right? If your Q is equal to 0 and you are supplying S equal to 1 here, then it is going to convert your 0 to 1. So that means your output Q is going to be set to 1. So you can check both the condition. Understand this thing, everyone, what I'm talking to you here. I'm saying you that suppose I'm giving R equal to 0 and S equal to 1. And with that, initially, let us say if I'm having Q equal to 0 and Q bar is equal to 1, then what it will be doing next output, it will giving you output 1 at Q and Q bar is going to be 0, right? But let us say my Q already 1 and Q bar is already 0, and I'm supplying the same input here, that is R equal to 0 and S equal to 1. Then what will be happening next output? Your 1 will remain as it is 1 and Q will remain as it is 0 Q bar. It means your output will not only depend on what input you are supplying. Your output is also depending on what type of input you have given earlier. I hope you're getting what I'm going to say here. And that is what we call it as a past input or past output. So in the flip-flop or in the latch, here what we are talking, your output will be depending on present input as well as the past output, or you can say past input condition. And that is why it is having the memory space there, and it will be able to store that information, that what was the last input has been coming to this circuit. So is that clear to everyone? Right, so that's what here it is discussed. Now here it is coming to the timing diagram. Now what do you mean by timing diagram? You look at here the diagram shown here. This timing diagram is showing you the inputs and output condition. You look at this circuit, R and S are the input signals, Q and Q bar is the output signal. So what the change will come in that? You can see here, S and R, here S equal to 1, R equal to 0. And you can see that Q is equal to 0 and Q bar is equal to 1. Okay. So if you check it here, you can say that, let me just take it here from the diagram so we can discuss it here. Yeah. So I'm saying this one, that these signals are the input signals S and R, and this signals Q and Q bar is the outputs, right? So these are the output signals and these are the input signals. Okay. Now, as we have discussed earlier, R and S, that is full form is set and reset. So when I want to set my output, here you can see this is the set condition. When your Q is equal to 0, it is, you may consider like a active low condition, right? Active low means when it is 0, you can say it is to be set, and when 1, it is called to be a reset. That is what here in timing diagram it has been said. So here R equal to 0 and S equal to 1. That means it is going to reset your output. So you can see that Q equal to 0 and Q bar equal to 1. So that is going to reset the output. Are you getting my point? Hello everyone. Please don't be get confused here. This timing diagram is shown with the reverse notation. That is, when S is equal to 0, it is considered to be an active high signal, and when S is equal to 1, it is considered to be an active low signal. That means this is logic 0, or you may call this is a low signal. In digital, what we are having low and high condition. So here 0 is considered to be a high condition and 1 is considered to be a low condition. That is for all the signals R, S, Q and Q bar. All of them are working with this, right? So when I say 0 means you consider it to be a high, and when I say low, it means it is a 1, right? So here for the first case, when I say S equal to 1, it means your S is set to be low condition. And when R equal to 0, you can consider to be a high condition. That means in this table, if we just look at here in this table, if we are talk about this first condition, let us say this R equal to 0 and S equal to 1 condition, right? That is what a set condition. And a third condition, R equal to 1 and S equal to 0, that is called a reset condition. So if you take about this third condition, that R equal to 1 and S equal to 0, whatever thing going to happen, that will happen here when R equal to 0 and S equal to 1, because here there is a reverse consideration in this timing diagram. Okay, so that is what here I am showing to you. So here you can see that output will be set here in the first case. Now in the next cycle, if you are applying both are 1 1, that means both are logic low, right? 1 1 means both are logic low, and that is what no change condition. So you can see your output Q remain as it is, what was previously here, and Q bar also remains same, what was previously here. So there is no change in the output came here, and that's why it is called here no change. After that, in the third stage or third cycle here, we have given S equal to 0, that means logic high, and R equal to 1, that means logic low. So it is going to set the output. So your output was 0, so it will be setting it, so it will be making it to 1, right? And that's why you are getting here output 1, and this will be going to be 0. Okay, so that's what the reset condition here. Then after again, when you supply both are logic 1 1 as it is, that means both are logic low, so there is no change, so you will be getting no change in the signal. Whatever output is there, that will be remaining same in the next clock pulse. Okay, but this is the condition when both 0 0, both are 0 0 means if you set both the inputs high, 0 0 means logic high, then your output can be 1 or 0 for Q and Q bar both, and that is why it is considered to be an invalid case. So are you getting this, how this timing diagram is going to work? See, in this timing diagram, on x-axis we are taking the time, and on y-axis we are taking the condition of that signal, whether it is logic low or logic high. Based on that, you can predict and find what the next output will be. So you have to look at for previous input also. So in timing diagram you can see, and here each section of this timing diagram is considered to be a span of 1 clock cycle. So are you getting understanding about this timing diagram? Hello. Are you able to understand this one?
Yes, sir.
Why it's taking too much time to give me reply? Hello everyone, I'm asking to you all.
Yes, sir.
Yes, sir.
Okay, so this is what about your experiment number 9. We are supposed to learn about this latch, how it is going to be set and reset, what is the logic condition for that, what are the valid inputs and what are the invalid inputs, when the output is going to be set, when the output is going to be reset. So that all thing we have discussed, and the timing diagram also I have explained to you just now. So now the task starts for your side. I'm giving you the link for this virtual lab. You will be verifying it through virtual lab. Let me first show you and then I will be sharing you the link. So here in the simulation side, you will be going to have this one window only here. So here you look at here, there are two NOR gates are required. So one IC7402 is taken, and in that only two NOR gates are connected with the cross connection. Two inputs R and S are given, two LEDs are given here at the output side. You can connect the battery, and then based on the condition of your input and output, right now both the inputs are 0 0. So you can see that right now output Q is set and Q bar is 0. So you can just if you want to add that condition, you can add it over here, right? And here timing diagram is also going to be developed. Suppose I'm changing the input, let us say R equal to 1. You can see that your Q get 0 and Q bar get 1. So if you add it here, your timing diagram is going to be prepared like that here. Okay. So with all that condition, when I set both is equal to logic 1 and add together, it will be giving you message like it is an invalid outputs. So it will be not taken there, right? Again, you can add the remaining parts and you can understand with the timing diagram as well as truth table and as well as here verification of LED. So what you have to observe here is you have to observe the table which we have learned here. That is the truth table of this logic gate. That is this one. That what is the NOR gate latch and how it is going to output set and reset. So this condition you have to verify there. That simulation tab will be of a logic low kind of the development. So you consider this table to be reverse, right? That means when R and S, what I mean to say is reverse means in this table wherever 0 you convert it to be logic 1 and 1 to be converted to 0. That is called logic, negative logic, or you may call reverse logic. So that virtual lab is showing you that thing, so you verify it accordingly. Okay, so now let me just share you this link with all of you, so you all verify it. Okay, I just share link in your chat window. You can just open this virtual lab in your device and just verify this NOR get latch. Once you're done with this, let me know so we can start with our next experiment number 10. And if you have any doubt, that we also can discuss. Okay, I think most of you have done it now. So can you just have a sharing by Subham? Subham, can you share your screen? Subham, just turn your mobile. Yeah. You just tried, Subham. I think most of students have replied me that done. So they have opened it and done it. So you just try it. Okay. Meanwhile, Subham is getting done. Let's Aditi, can you share your screen? Hello, Aditi, are you there?
Yes, sir.
Yeah. Please share your screen.
Sir, my website is not loading.
What is not loading?
It is not loading.
Site is not getting open. You just try it because
Yes, sir.
everyone else has already done it.
Yes, sir.
You try to open in another browser if it is not getting open in that particular browser which you are trying with. Okay, Naisargi, can you just start sharing your screen so that Aditi and Subham can see how it is getting open? Just rotate your mobile. Yeah. So look, Aditi and Subham, it's getting open in Naisargi's device. So I think it should be get open in your device also. Right. So you need just need to check about this table and the timing diagram for that circuit. When it is not changing the output, when your output is getting resetted, when your output is getting set, that you have to see here. Right. So when R is equal to 1, S is equal to 0, your output is getting reset. You just look at the timing space also. Here, if you just look at the very first step, your output is taken 0, Q bar is set to be equal to 1. Right here, the first two input R and S both are 0 0, and at that time your outputs here, if you just go color wise, you can see that first condition is Q bar, and that is mentioned here on the side also. Okay, so Q bar is 0 and Q is equal to 1. That is the initial condition. At that time, your R equal to 0 and S is equal to 0. That is for the first timing step 0 to 1. Right? Blue signal is for input R, red is for input S. This purple signal is for output Q, and this green type of signal is there for Q bar. Right? So accordingly, you can see the timing diagram also. And if you just look at in the table, truth table here, for the first case, R and S both are 0. For second case, R equal to 1 and S equal to 0. So you can see that your output before that, what was Q here in table, you can just see Qn minus 1 is mentioned. That is the output before you have applied this condition. Right? So that is Qn here. What was there in the first condition will become Qn minus 1 for the second condition. So here serial number mentioned 1, 2, 3, 4, 5 is the timing steps 0 to 1, 1 to 2, 2 to 3 like that. So accordingly that you can verify it. Okay. So for 0 to 1 timing step, you can say the serial number 1 will work there. So for that your Qn and Q bar is there at the present output. And for the second case, you can see that is R equal to 1, S equal to 0. That is for the timing step 1 to 2. And at that time, what you can get at the output side, your Qn becomes 0 and Qn bar will become 1. That is what you are getting reset condition. So Qn minus 1 and Qn minus 1 bar is your past output. So that is given here in the table. So that is helping you to understand the present output, right? So here Qn is the present output, Qn minus 1 is the past output. So if your present output is changing from past output to present output, then that change will be mentioned either reset or set. If you have supplied a invalid input, that is R equal to 1, S equal to 1, then it will be showing you there is invalid condition on the input side, right? So in that case, you can see here Qn and Qn bar both become 0. So that is not a valid condition. Okay. And when you are supplying 0, 0, that will be giving you no change condition. If you are supplying S equal to 1 and R equal to 0, you will be getting set condition. So in this way, you have to verify this latch that when it is getting set and when it is getting reset. That means when you are getting your output Q equal to 1 and output Q equal to 0. Okay, that's fine, Sergey. Everyone, please do it like this and just get it verified so that you will be able to understand that how this latch is working. Have it get open in your device, Aditi? Subham?
Yes, sir.
Yes, sir.
Yeah, just get it open and verify it, and so that it will make you to understand how the working of this SR latch is going to be there in your circuit. Okay, so let me just now start with the next experiment. You do this at your time now. Okay, so I just discussed about the basic thing required for this experiment number 9, that is the NOR gate SR latch. Now let us take you to the next experiment number 10, that is the verification of another latch or flip-flops. So let me just share my screen first. Okay, so here you just look at this. Our next experiment number 10 is this one. The aim is to verify the truth table of RS, JK, T and D flip-flops using NAND and NOR gates. So here you can see the RS flip-flop is there, which we have learned in the previous case or in the previous experiment. But here in the flip-flop, your flip-flop is just kind of latch only, but it will be having a enable signal. Understand this thing? Flip-flop will be having a latch inside, but it will be applied with one more signal that is called enable signal. It means unless your flip-flop is enabled, your latch will not work. Means it will be getting no change in the output condition. And that is why it is called flip-flop. Okay. So there are 4 types of flip-flop we are going to learn today. That is RS flip-flop, JK flip-flop, T flip-flop and D flip-flop. So what is that? Let us start with the first one, that is RS flip-flop. So you look at here. Now what is this RS flip-flop? If you look at the diagram, let me just take it this in the next slide, so where I can add notation. So just look at here. This is what your RS flip-flop. Why it is called flip-flop? This flip-flop is having 2 parts. That is, it is having, this is your RS latch that we have discussed in the previous experiment, right? In this green bracket or whatever thing is there, a cross-coupled NOR gate, you can see that is nothing but it is a RS latch or SR latch, what you say. And here this RS latch is added with more devices, that is the logic gates here. You can say logic AND gate over here, AND gate number 1 and AND gate number 2. So these two AND gates are added here. Now this AND gate will be supplied by your S input here and R input here. And second input to this two AND gates are coming from the single input, that is what we call it is a clock pulse. This clock pulse is nothing but it is the enable signal. Enable signal means unless this clock signal is having logic high or logic 1, your input given to R and S will not be applied to your latch. I'm discussing about, see, ultimately this latch is there here, RS latch or SR latch, whatever you say, right? This is your RS latch. And this RS latch is going to set or reset your output Q and Q dash here, as per the discussion of experiment number 9, what we have just completed, right? If your input R coming here, let me call this is input R dash, okay, and this is what I can say S dash. So input R dash and S dash is going to decide what will be there at the output Q and Q dash, right? If you are setting your R dash and S dash is equal to 0, 0, your Q will remain as it is, means no change will come in that. If you are setting R dash is equal to 1 and S dash is equal to 0, your Q will be set to equal to 0 and Q bar is equal to going to set to equal to 1. It means the next part after your AND gate number 1 and 2, it is working similar and exactly same what we have just completed, that is RS flip flop, RS latch. But here these two AND gates are connected to add a enable signal. That means now I just want to get my output Q affected only if I have given enable signal. It means if I'm not enabling my circuit, then whatever R and S is coming, whether it is 1 1 0 0 or 0 1 or 1 0, in any of that condition, my output Q and Q dash remain as it is, no change will come in that. That's why there is the importance of enable signal here, right? So you can see here in the table also that when the clock signal is shown here, here X means clock signal is don't care. X we are using for representing don't care, means whether it is clock signal is logic high or logic low, whatever condition is there. In both the condition, if your S and R 0 0, then there will not change in the output. So previous output will remain as it is. Okay, that is what the table you have already learned about SR latch. Then after here it is shown by arrow, a clock pulse is coming. Why it is shown arrow? Arrow is shown to show you a rising pulse. Suppose this is the clock pulse, right? Suppose this is the clock pulse, means it is a square waveform. So if there is a clock pulse signal is like this is called the rising edge, this is called the falling edge. This is the rising edge, and again this is the falling edge. So this rising edge is considered here to show that your clock pulse has been arrived, right? So that's why that is showing you the upcoming arrow. So it's a rising edge of clock signal is shown. So if your enable signal applied here or clock signal applied here, if it is a rising edge, means it's showing you that it's a rising edge triggered RS flip flop. So whenever there is a rising edge of clock pulse will come, your input given to this R and S will work, otherwise not. Why is that so? Understand this one. Because if you are setting your clock signal to be 0 here, one of the inputs of these two AND gates are going to be 0, right? And now whenever AND gate is getting one input 0, your output will be always 0, isn't it? So when your clock signal is 0, your output which is given to this clock signal, RS flip flop, here is going to be 0, and here also it is going to be 0, because your one of the input of both the AND gates are 0 0. So that will be considering this first condition, and that's why your output will not change in that case. But whenever you are giving the rising edge, that is for these three conditions, means if your clock pulse is applied here, that means your input to this AND gates are 1 1 here, then whatever you are giving, if your S is equal to 0, then output is 0. If your S is equal to 1, then output is equal to 1. Means this AND gate will allow this R signal to go to R dash and S signal to go to the S dash, like this. So according to the value of R and S, your Q and Q bar is going to be either set, reset, or will be kept as it is without change. That is what the purpose of this enable signal. So are you able to understand this RS flip-flop? It is just like a RS latch only. That's what we have just discussed. But only thing we have added here is the two AND gates and one more signal, that is the enable signal. And that is we are supplying by clock pulse. So whenever there is a clock pulse is coming, that AND gate will be allowing your R and S to go into the R and S of your latch. And that's why your latch will be either set or reset. So are you getting this, all of you? Hello, everyone.
Yes, sir.
What about others? After asking the question, I need to wait for the answers for more longer time. Still, I have only one answer. What about others?
Yes,
You all
sir.
understood?
Yes, sir.
So this is what the difference between your latch and flip-flop. Latch will not have any kind of enable signal, but flip-flop will always have, right? So now let us go with the next flip-flop. This is what you have understood RS flip-flop using NOR gate. That means you can see this is a NOR gate having connection, cross-coupling connection here. Now, the second thing we want to discuss is about D flip-flop. So you look at here the D flip-flop. This one is the D flip-flop. Now, what is the difference between the RS flip-flop and D flip-flop? You look at here this circuit, you can find the difference. In the RS flip-flop, we were having two inputs, that is R and S, right? But here in the D flip-flop, this combinedly is your D flip-flop, right? This is a combinedly known as your D flip-flop. But if you go inside, you can say this is what? This is your SR latch. So ultimately, D flip-flop is also going to have the SR latch inside. But before SR latch, it will be having two NAND gates. You can say this is the NAND gate number 1 and NAND gate number 2. So let's say NAND gate number 1 and 2, like this. And one NOT gate is also used here. So what is here? If you look at in the previous case of SR latch, that we are giving either set condition or reset condition at the output side, right? Means when R equal to 0 and S equal to 1, it will be giving you output to be set. That's what the condition for this SR flip-flop. Let me just draw that table here just beside here so you can get it idea. So I'm talking here. Okay, so first of all, let us say your R is here. Then S is here. Then QN. And let us say here it is remarks. So when your R is equal to 0, S is equal to 0, here we were getting Qn minus 1, that is last output. So you are getting no change here. So that is what we call it as a no change. Okay. When your R equal to 1, S is equal to 0, your output is going to be 0, and that is what we can say it's a reset condition. Right? When r equal to 0, s is equal to 1, we get output to be 1, and that's what we call it as a set condition. And when both are 1 1, it is called invalid condition. So we are calling this as a invalid. So this is the truth table of your RS flip-flop or RS latch, right? Now in this RS latch, we are converting it to a D flip-flop. So what do you mean by D flip-flop? So here D flip-flop is doing what? It is considering only one input, and that is called data input. D stands for data. Okay. So that data input, if it is coming 1, then it will be supplying 1 over here, and through this NOT gate, it will supply 0 over here. If your data input is 0, it will supply 0 over here, and through NOT gate, it will supply over 1 here. That means you have seen in this table of RS latch that they both can never be 1 simultaneously. That is what an invalid condition. So in this data flip-flop, by connecting a NOT gate like this and making your single input, data input, we are able to avoid this condition, that is 1 1 condition, because now you have only one input, and that's going to decide your S and R, right? So they both never going to be 1 simultaneously. And that is why it is called a data flip-flop, and that is D flip-flop. So here there is a NAND gate is used, and this is the clock signal is given to this NAND gate. So whenever you are setting D equal to 0, you can just now look at your table. When data input is 0, here it is going to reset condition, and clock is also 0. Then your output Q equal to 0 and Q bar is equal to 1. Right? Then if your D input is data input is 0 and clock signal is logic 1 and reset condition is 0, then you will be saying the same condition here at the output side. But when data input is 0 and if you are giving your reset condition to be 1 and clock signal to be 0, then you are getting again same condition here at the output side. So what this means, sorry, this shows you the table that when D input given, that is going to decide your output condition, means whether your output get resetted or not. In short, when data input is logically 1, you look at here for this condition, your output is going to be set only if clock signal is given, right? Otherwise not. If there is no clock signal and data input is 1, your output is going to be remain same as it is. It will be not changing there. Sorry. So this NAND gate, you need to remember this truth table also, NAND gate also. Let me just clarify here with this, so it will be better for you to understand. In short, let us take example with the data input logic 1 here. Sorry. Suppose I set the data input to be logic 1. And if my clock signal is also set to be logic 1. Okay, clock is also 1 and data is also 1. That means my clock signal is given. So this clock signal 1 will come here at both the input of these two NOT gates, NAND gates. And this data input 1 will come here, and through this NOT gate, it will come 0 over here. Okay. So this first NAND gate will getting 1 1 on both the inputs. That's why this NAND gate will give you output logic 0. So your S will become 0. And here 1 0 condition is coming. So you are getting 1 over here, because NAND gate will give you output 1 when there is one input is 0 and other is 1, right? So what this SR latch is getting now, S equal to 0 and R equal to 1. So what you are getting, your output Q is going to be resetted. Means Q is equal to, because R is 1 and S is equal to 0 for the SR latch. So you are getting here output Q to be reset and S to be, Q bar to be 1. Okay. Likewise, you can check it for other case that data is equal to 0 and clock signal is 1. Then what will be the case? Then here there is a 0. So you are getting S equal to 1. And here there is a 1. So 1, 1. So we make your R equal to 0. So your output will be set. Okay. And if clock is not there, means if your clock is 0, if clock signal is 0 here, then whatever data you are giving, D equal to 1 or 0, your output coming to S and R, that both is going to be 0, 0. And that's why your Q remain as it is. So are you getting all this? Hello? Hello? Am I making this thing clear to all?
Yes, sir.
So only thing you need to learn in D flip-flop is we are avoiding the simultaneous 1-1 condition coming on the input side by connecting both the input to a single input, that is the D input, by putting a NOT gate in between there. So either they both can be 1-0 or 0-1, but they never be either 0-0 or 1-1, right? So that is what the condition here we are having in this case. So that is what the D flip-flop. Then next we will be having here, that is the JK flip-flop. Now here this JK flip-flop is also developed to avoid this that simultaneous 1-1 condition. So you look at this flip-flop connection and the table. Just a minute. Let me take it. Okay, so this is the JK flip-flop table and the diagram you can see. In this JK flip-flop, we require to have two AND gates, number 1 and 2 you can see. That is for 3 input terminals. Now here 3 input signals are required for this AND gates. So now out of these 3, 1 input is connected to K here, 1 input to the J. Like in RS flip-flop, we were giving name R and S. Here it is J and K. Okay. So one of this input J and K is going to set the output and other is going to reset the output. That means when J equal to 1, your output is going to be set, and K equal to 1, it will be reset. In this also there is a RS latch. See, all the flip-flops are having their RS latch inside. Right? So this is a basic building block of all the flip-flops. So RS latch is still here also. But that RS latch is connected with another gates, AND gates 1 and 2 also here. But these AND gates 1 and 2 are getting input from this output. That output Q is connected at the input of this AND gate number 1. And Q dash is connected at the input of AND gate number 2. Okay. So, and other inputs are clock pulse and J and K. J is for set condition, K is for reset condition. But here in this configuration, we are not going to have problem with that number 1 simultaneously. Means if you make your J and K both equal to 1, 1, then also there is no invalid output will come. Your output will be a valid. So that is what the advantage here will be getting in this JK flip-flop. So here, how this is going to work? Ultimately, we are going to set or reset your output Q and Q dash by using J and K input if clock pulse is present. So you can look at in this table also. Here, the first case shown here, there is no clock pulse. So if no clock pulse is given, then whatever J and K value is there, whether they both are 1, 1, 0, 1, 1, 0 or whatever it is, there will not be any change in your outputs, right? So it will be remain as it is. But if the clock is present, here it is shown, see, in all this case, your clock is present, means your clock is logic 1. So when clock is logic 1, Then you have to see that what is your J and K. If your J and K is 0, 0, and here it is present state and next state mentioned in the table, you can see. So Q dash present state, if it is 0, 1, then the next stage will be 0, 1. If it is 1, 0, then the next stage will be 1, 0. Means there will not be any change. What it is, you are just looking here. Suppose I'm saying about this thing. Let us say my J and K both are 0, 0. Okay. K is also 0, J is also 0, and clock pulse is 1. That means clock is present. So in that case, you will be getting 1, 1 over here. Here your K is 0 coming to this AND gate, and J is coming 0 to here this AND gate. And suppose your output, this is present state. Let us say present state is 0, 1. That is your Q equal to 0 and Q bar is equal to 1. This is the present state, suppose. Okay. So this present state, Q0 will come here at this input, and Q dash from here it will come here, so it will be 1. But as you can see, one of the input of both the AND gate are 0, so your output coming here is 0, 0, and that's why your flip flop latch, because of this to NOR gate, will make your output to no change because both are coming 0, 0. So that will remain same. So this will remain 0 only and this will remain 1 only, right? And if it is 1, 1, means if your output is 1 and 0 previously, then this 1 will come here and this 0 will come here. Then also your output to AND gate 1 and 2 will be 0, 0. So there is no change. So that is what the condition we are talking for this first case. That if your J and K are 0, 0, in that case, whatever your output state, whether it is 0, 1 or 1, 0, that will remain same. No change will come in that. But if you are keeping J equal to 0 here and K equal to 1, then it is going to change your output state. Like here you can see that. Okay, let us just me change that inputs and output condition. So I can show you that what happens inside. I'm setting J and K input. According to that, I want to see what is the change at the output side. Suppose right now present state of output is like this. Q equal to 0 and Q bar is equal to 1. And I'm going to apply for the first case here, that is your J equal to 0 and K equal to 1. So I'm making J equal to 0 and K equal to 1. So this clock pulse 1, 1 will come here, K equal to 1 will come here, and J equal to 0 will come here. Okay. Now present state is Q equal to 0, so that Q0 will come here, and Q dash 1 will come here. So you look at here, as your J and K both are 0, 1. So you can see this, that your present state is 0, 1. So Q is 0 and Q dash is 1. So what that will give you output here, JK11, and this AND gate. Right now it's going to reset the condition. So sorry, which was I talking? J equal to 0, K equal to 1. Yeah. Here either there is a mistake in writing J and K or something, because this is also giving 0, 0 condition, because 1, 0 is coming here also and 1, 0 is coming here. Either that J and K should be reversed. Maybe J, K input are reversed. Just a minute, let us check about this diagram. I think there is a cross connection is coming at the output side. Let us me take another diagram from the net. This diagram is having something mistake in the connection. So let us me just take a diagram of JK flip flop. Okay, so look at this diagram which I just taken from the net site. So here something change in their connection. Yeah, J is coming here upside, K is here downside, right? And Q bar, they are connecting here cross connections. Right? Q bar is taken from here. Right? So that is a change. So you understand this connection change here. Okay. So there is something wrong in this. So you either need to consider J over here, K over here. Sorry, reverse. It is already there like that only. You consider J here and K here, right? That is the thing required. So J going to be 0 here and K going to be 1 here. That is what the condition we are talking. So that will make here 1 and here 0. So here second AND gate will be getting all 1. So here you will be getting 1 and here you are getting 0. So 1 0 condition will going to be there. So S is going to be 1 and R is going to be 0. So you are getting set condition. So this will be 0 to 1 and 1 to 0. Are you getting all of you? So this is the change in the diagram. So that is small mistake is there. So you have to connect accordingly. Otherwise, it will be giving you no change in all that condition. So this is the correct diagram which I just taken for your reference, right? So that you can replace here. And here output side cross connection will be taken if you are using NAND gate over here, right? If it is AND gate, then it will not be cross coupling. It will be same as it is what here it is. So am I removing this confusion to everyone? Only the thing is that your J and K is reversed on the input side, right? Hello. Are you getting it what I'm saying, or still any confusion in the diagram? As I was explaining, I found that there is a change in the position of J and K. That's what I just clarified with the diagram which I taken from net. So are you getting it or not? Hello? Can I have a reply from your side? Okay. Okay, fine. Thank you. So just understand this thing, right? There is small change in the connection. You need to consider this J and K reverse. So that will make you to understand and verify this truth table. Otherwise, you will not be able to verify it. So now you just check about this. When J equal to 0 and K equal to 1, that's what I'm saying. That when J equal to 0 and K equal to 1, it's going to give you set equal to 1 here and R equal to 0. So you will be getting set condition. And for the next condition here, if you are making J equal to 1 and K equal to 0, you will be getting reverse condition, right? And the 1 1 condition is need to be understood here. That when you are giving J and K both 1 1, at that time what will happen? At that time your output is not going to be invalid. It is going to be toggle. You can see this one. The last value in the table is written here. It is a toggle. Toggle means what? If your output is 0 1, it will be made to 1 0. If it is 1 0, then it will be made to 0 1. It means it will be changing. If it is 0, then make to 1 1, then 0. So in the case when you are making your J and K both 1 1, your output is going to be toggle. That is called the toggle state. Set condition, reset condition, and the third condition here it is introduced, that is called toggle condition. So that is only possible in the case of JK flip flop. It is not there in the D flip flop or RS flip flop, because in that case there is no invalid inputs are allowed to the given at the input side. But here in JK flip flop, you can apply both input 1 1 also, and that is going to do what? Sorry. When both the inputs are set to be equal to logic 1, your output is going to be toggle. Toggle means you understand the meaning of toggle. If your present output is 0 1, then next output is going to be 1 0. If present output is 1 0, then the next output will be 0 1, like that. So it is going to toggle whenever you are keeping your input both are 1 1. Is that clear to everyone? Hello? Hello? Okay. So now after JK flip flop, next flip flop is T flip flop. T flip flop is the toggle flip flop. T stands for toggle. Toggle, that is coming from JK flip flop itself. So T flip flop is not a new thing. From the JK flip flop, here we have separate J and K inputs. But in toggle flip flop, we are combining that J and K to make a single input, that is T. And T stands for toggle. So whenever T equal to 1, your output will toggle. And whenever T equal to 0, your output remains same as it is. So that is what your toggle flip flop here. And you can look at this table also. In toggle, you can see when T equal to 1, your output will be Q dash Q, means it will be toggling. And if your output T equal to 0, your present output remain as it is. But if your clock pulse is not given, so downside arrow you can see here in the last input. In that case, whatever toggle input you have applied, your output will be no change. So are you getting this? So this is about all the flip flops. RS flip flop, then D flip flop, then JK flip flop, and now we are talking about T flip flop. Ultimately, all these flip flop are having RS latch inside. But with this RS latch, we are putting some logic gate combination outside to represent a different flip flops at the output side. Okay. Now you can verify this all the flip flops with the virtual simulation here. So you can go into the simulation tab. There all the flip flops are here given the options. So let's say for SR flip flop. So when you click on that, you will be getting this circuit connections. So here you have to have AND gates. NAND gates. So this flip flop is developed using NAND gates. And so there is the three inputs, SR inputs and clock input, and power signal you have to make on first, and then after you have to check with condition. If your R and S both are 0 0, then what is the condition? You can see this, right? That your output will have no change. But if you make S equal to 1, and if you just edit, you can see that apply the clock pulse, right? If you have not applied the clock pulse, there is no change in. If you make your R and S both are 1 1, and still if you check it out, it will ask you to apply the clock pulse. Means unless you apply the clock pulse, your R and S will not be applied to your flip flop. That is called enable signal. So if you make your clock 1, then only you will be getting that both are 1 1, so it is invalid. If you make S is equal to 1, R equal to 0, and if you edit, again it will ask you the clock pulse. So I have to add it like this. So it will making the set condition, right? So this is how you can verify all the flip flops. So now will you be able to do it? Should I share this link to all of you that for the virtual lab? Hello. So let me share that link to all of you. Yeah. So now just open this link in your device, and you will be getting the option for verifying all that 4 flip flops. So you just get verified it. So that is going to be our experiment number 10. So all of you just do that verification, and if you're getting any query, any problem, you just ask me here, so I can just discuss with that. Okay. Yes, Nisargi, the simulation tab doesn't show the add button. But which add button you required in that? Okay, let us just try this link. All of you use this second link I sent to you. If it is getting in that, Nisargi, can you just start sharing your screen and show me that what happens in your login? Why it's happening like that? Because I'm opening the same link here in my laptop. It's getting that add button over there. Can you just click that space of that add button if it is working there without button over there? Can you just try to open in another browser? Okay, actually I'm getting that add button over here. So Subham is saying that it's showing. Can you just all of you, those who are not getting that add button in different browsers, so it may possible that issue of browser. Uh, okay, Vartika is also saying that it's showing. Subham is also saying showing. Subham, Vartika, are you using laptop right now or in mobile? Okay, Vartika is using in laptop. What about Subham? Subham is using in mobile. So Naistaki, it's not an issue of mobile. Kevir is also saying that it's showing to him. Okay, Chrome is not going to work. Yeah. All of you just change your browser. I think there is an issue of browser something. Right? Instead of Chrome, you can use another one, whatever it is there in your device. What happens now, Naisargi? Is it getting open or not? Oh, I think many of you are getting it open. So, okay, no issue, Nesrgi. You can perform it later on, whether it is in laptop or in your other browser when you install it. Okay, Kayur, can you just start sharing your screen so everyone else can see that? Hello, Kayur.
Yes, sir.
Yeah, start sharing your screen and show others that how it is going to be verified. Yes. So this add button is there in Kayur's screen. It is a D flip-flop. So when data input is set to be 1, but if clock is 0, then no change will come. And for the same input condition, if clock is 1, then you can see that set condition at the output side, right? And that you can check in your timing diagram also. Yes, this is for SR flip-flop. If clock is there 1, then only your output is going to be set or reset. If clock is 0, then whatever condition you are applying, you're getting 0 condition or no change condition at the output side. Yeah, this is for T flip-flop. You look at here, toggle. Toggle means if your previous input is 0 1, it will be getting output 1 0, right? So that you have to see. If it is 0 1 1 0 1 0, then 0 1, like that. Okay, so I think now all of you have understood this, and you will be able to do that in your device, and you will be able to complete this experiment, right? 9 and 10. Is it okay to everyone, or any difficulty in understanding these two experiments? Hello, everyone. Have you all understood this two experiment now, or any question in your mind to get it answered here? Okay. Okay, that's fine. So I'm getting yes from all of you. So you all have understood it. So now prepare your experiment 1 to 10, whatever remaining with you. And I think it is already extended date for submission. So those who have not submitted whatever experiments, so you just complete it and submit, right? In after completing this 9 and 10 also. Okay, so that's what all from my side today. Now you can just enter your attendance and then you can leave, and we'll meet again in our next session. So now you all prepare your experiment number 9 and 10, right? And submit in Canvas. And whatever experiment pending for up to 1 to 8, that also you can complete and submit. Okay, I think all of you have given your attendance now, so I'm going to end the session. Okay, thank you all.